Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
Before I start, did you get my coffee? This is what I mainly use our lab demo people for, and I always go to Zingerman's in the morning and have my coffee get me going before lectures, but I didn't make it today, so they got me some coffee. When did you get this coffee? Boy. So the question is, that coffee. How old is it? Unfortunately, I didn't pay for it, so I can't be fussy. Let's see. Is there something I could measure of this coffee that would tell me how old it is? That is, what's its age since its creation? Do I have any young scientists in the crowd? There should be some young scientists.
How about temperature?
Well, you're an old scientist. You would know that, of course. So all you young scientists, see what a lifelong study of science will do? You will get the right answers. Yes, temperature might be a good measure of the age. Let's see what the temperature of the coffee is now. Oops. Let's see. This is our baby thermometer from our medicine cabinet. I don't know where it's been recently. Gee, I don't want to put it in my coffee and drink it, probably. Can I measure the temperature without touching the coffee? Yes, we can measure its black body radiation spectrum. This was originally developed, this is an infrared thermometer, non-contact, originally developed for the steel industry to measure steel, molten steel temperature in a blast furnace where you really didn't want to send somebody in to put a thermometer on it. So you could do it with this infrared spectrometer. And so if I point it here, down there, without touching it, I get that it is now pretty darn cool. 94 degrees. If you heat something up, like a lamp over here, you get a color. And you start with a dull red color, which corresponds to, let's say, 3,000 degrees Kelvin. And as you heat it up more and more and more, it gets brighter and brighter, but its color also changes. In fact, its peak color shifts down to the yellow and then the blue and then into the ultraviolet, and it keeps going. That way, it also will keep going that way. If I turn this lamp way, way down, in fact, you're not measuring any color there right now because your eye is only matched to the sun's spectrum, evolution again, and you only can detect that with your eye, which is good because you don't see a lot of superfluous stuff and you can sleep at night. But if I measure that, I do get that it is 110 degrees, even though you don't see that. Okay, so we can measure temperature by measuring the wavelength of the emission. Now, we don't have to find the peak wavelength. We can measure down here and get a curve. All these curves follow a well-known quantum mechanical law from which we can deduce temperature just by observing the black body color of an object. So this is the non-contact thermometer I talked about, infrared radiation thermometer. My usual coffee, 156 degrees. Thus, if I know the present temperature of the coffee is 94 degrees, and I have a model and data of how the temperature decays with time, I can deduce its age. So I'll have to have a few assumptions. That the coffee is in a certain type of cup. It's a standard Zingerman's cardboard cup. The coffee, when poured, starts at the same temperature. That depends on Zingerman's. They're usually pretty good about that. The coffee is black without cream, or it's with cream, and I know which one I'm using. And I have the same amount of coffee in the cup. So those are my controlled variables. Then the temperature must decrease uniformly at a known rate. So I'm going to have to know how the coffee cup temperature decreases with time. If you drink a lot of coffee, these are things you should know. Also, that the coffee cup is not in a rocket ship traveling near the speed of light. That is usually a good assumption, not always, because we know Mr. Einstein, our beloved physicist of the year, last year, tells us that there's a time contraction that things age slower when they are moving near the speed of light. This is to keep the speed of light a constant and the maximum speed you can ever have in the universe. This leads to the so-called twin paradox. So this is a demonstration I've been wanting to do for about 30 years. I can do it today. So here's our twins. Down. They're not identical twins. Some interesting genetics there. We have to ask their parents about that. But I'm going to send one off in a rocket ship. Here's my rocket ship. Best I could do on short notice. And I'm going to send her. She's a physics student, by the way. She's been eager to look at a star, the properties of a star 10 light years away. So she's going to go at the speed of light. This rocket ship can go at the speed of light. Amazing. We've developed some new things for that. And she's going to go off through that door and go visit a star 10 light years away. And then she's going to come back 10 light years from now, or a total of 20 years round trip. So can you do that? Are you prepared? Have you passed your test? Do you have your astronaut driver's license? OK, good. Then can you go off? There she is. She has it. OK. Now, meantime, our twin, a little faster, non-identical twin, there she goes, is going to go off to school. She's a professional student. She's undergraduate now. She loves U of M so well, and Ann Arbor and Zingerman's, that she stays here for 20 years in school. She gets her BS, PhD, MD, MBA, LL, whatever. And so she's going to go off to school for 20 years. OK, fast forward 20 years. Could our twin come back? So she's been gone for 20 years, but traveling near the speed of light. She's got this factor down here working for her. Guess what? She's aged only a year. Her clock has slowed down. Now, it doesn't matter what kind of clock. It can be a heartbeat, a biological clock. It has nothing to do with clocks. That's a misconception. It can be a biological system. And meanwhile, our other twin, I believe, has finished school finally. And here she is. Now, what's amazing, this is true. This will happen. We just need a rocket ship that goes fast enough. So one of the other assumptions, does the coffee temperature decrease uniformly with time? Being a scientist, of course, I know that because I've measured it. So here's the decay rate of the coffee in that cup, standard Zingerman's cup, as a function of time. And you can see it does satisfy the condition that it uniformly decays with time. Therefore, I know the present temperature of the coffee is 95 degrees. Therefore, it's 40 minutes old. And they came in, I think, about 9:30, 9:45, so that, I guess, checks. So there we have an age curve. This is what we're going to use now for the rest of the lecture. The curve is a typical exponential decay curve, the kind we're going to see exactly in radioactive decay. It has to be a uniform decay curve. So what does that mean? It means it can't look like that. I can't stick more coffee in it, this time heat it up again and then have it. Because here I would have 1, 2, 3 temperatures, all at different times. So just measuring the temperature, you see, if I said the coffee was, well, let's see. If I said the coffee was 50 degrees, let's say, this is actually Coke or something with ice. I would say that, well, it's either here, or it's here, or it's here, you see, because there are 3 solutions for 50 degrees. So it can't look like that. So cooling curves, that's one way to determine age. So let's see how this can be applied to the Earth, the stars, and the universe. A little more interesting than the cup of coffee. Okay, so here's the Earth. How old is the Earth? So, Lord Kelvin, after which the Kelvin temperature scale is named, in about 1895, tried to do this before radioactive dating was available. So he got an age based on a model. He built a model of the Earth out of rocks and metal and whatever, heated it up and let it cool. Then he tried to scale it using some thermodynamics, et cetera, et cetera. Doing that, he gets an age of 40 to 100 million years. Now remember, an English bishop in, 1750 had declared that the Earth was created October 23rd, 6,000 years ago or something. So Kelvin got into trouble here because he says, wait a minute, the Earth is millions of years old. Okay? Well, there's a problem with that. Because a young man, Charles Darwin, had just proposed the theory of evolution, which says that things change over time. Things evolve. But to do that, you need a very old Earth if you want all those changes to take place. Because we don't see major evolutionary changes in our lifetime, so obviously we need a long, long time for any evolution to occur. So 100 million years isn't going to do it. And Thomas Huxley? T. Huxley, who was a supporter of Darwin, said, "Lord Kelvin, you must be wrong. I believe in the theory of evolution. Your age has a problem." But amazingly, a lot of scientists repeated Kelvin's work using different techniques, and they all got 50 to 100 million years, some got 200 million years. This is kind of evidence for pathological physics. A well-known feature in physics. No one wants to disagree with a famous scientist. If you get a negative result that disagrees, you generally don't publish it. It's put away in a notebook somewhere. If you get, and referees may not accept it either, those that judge publication quality, etc. So no one disagreed with Kelvin, so for many years that was the age of the Earth, 100 million years, plus or minus 50 million years or so. And there are lots of publications on that. Okay. But unknown to Kelvin, and only discovered in the 1890s, was nuclear radioactivity. See, Kelvin assumes that there's no new heat source in the Earth, that the Earth just was a molten rock or molten metal and just cools down. But if there's a heat source in the middle of the Earth, some sort of lamp inside, well, the Earth is going to stay warm. And you will deduce a younger age. Well, radioactivity is a heat source for the Earth, and it's one reason why your water pipes don't freeze, amongst others. Marie Curie is the person who coined radioactivity. She discovered the basic forms of radioactivity, discovered new elements, including radium, polonium. She was not French, of course. She was Polish. She won 2 Nobel Prizes, physics and chemistry, yet was denied membership in the French Academy of Sciences. She later got in via a back door as in the medical French Academy of Sciences. Long history, probably our first example of discrimination. Okay, so if you include the heat due to radioactivity in rocks, and we're going to see using the radioactivity itself, the decay products, we can measure the age of the Earth, and if you do that, you get more like 1 billion years. So Huxley was correct, the Earth is very old, and that makes evolution plausible, at least to most of us. So Charles Darwin was redeemed. He was not a famous scientist, of course, at that time, so people did not take evolution seriously in the 1900s, because the Earth was young at that time, 100 million years. Okay, stars in the universe. Well, we actually have better models for stars than the universe itself. The Earth is a difficult problem to treat cooling because it's very complicated. So we have nuclear reactions that form the elements. We know how those goes. We can measure them in the laboratory. That's the sort of thing I do. So we pretty much know how helium comes from hydrogen and how other elements are made through nuclear fusion reactions. All can be studied in the laboratory. Therefore, we have a good history of how stars are made and how the universe evolved, and basically how simple elements are made. So knowing that, and also the fact that we have a nearby star we can study in pretty good detail. We just go look, send satellites, etc. But people could do that even in the early 1900s. We know that after Einstein came along, E equals mc squared, we know how the sun makes its energy. It's hydrogen fusion, basic nuclear reaction taking place here. And eventually all that light gets out to the surface. Actually, it takes millions of years, by the way, which is interesting. And we also know the temperature of the sun, and we know its history pretty much. Okay? Now, there's a certain class of stars called white dwarfs. These are smaller stars than our sun in general, I believe. I'm not an astronomer, so any astronomers here, they can correct me. I think I see a few back there. And based on their nuclear reaction history, we know that they are stars that don't explode. They just ignite initially, and then they just burn, 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 and then cool off. And there's a good model on how that happens, and so there's a cooling model for certain types of stars. And of course, now we can trace back the temperature of all these stars just by looking with better and better telescopes, again, using not an infrared thermometer, but other types of thermometers. And what we have to use is a big telescope with a spectrometer on the end to give us the temperature, and we can do that. Here's a big spectrometer, 200 inches at Palomar. And with that, we can measure the temperature of these old, cooled-off stars. And we get a wide variation, but the oldest stars we see are 12 billion years old, based on the cooling model for these stars. So here we have a first estimate of the age of the universe, 12 billion years. Again, there's a cooling model. So let's see, is that consistent with other things? And one question, of course, are these old stars really there at the start of the universe, or did the universe come even earlier? So does the universe itself have a temperature we can measure? It's not obvious. And is there a cooling model for the universe? If we know the temperature of the universe at a certain time and have a cooling model for the universe, how the temperature changes with time, we can go back and use our cooling curve to deduce the age of the universe. So first attempt, I'll just take my infrared spectrometer here. Go find a nice dark patch in the sky and point it up there. Well, that measures the temperature of the atmosphere. Doesn't work. So we have to use other types of radiation, and the answer is yes, the universe has a black body temperature, and it was discovered by accident in the 1960s. So in the 1960s, we had put up satellites, and we wanted to, AT&T, particularly Bell Labs, wanted to use the satellites for long-distance communication, and they would use big radio dishes like this. This is a microwave radio dish, to observe the satellites and try to track phone calls using the satellites. But the phone calls were very, very noisy. They heard a hissing sound in the background, something like sss. And it was everywhere they pointed. So they thought it was pigeons nesting in the microwave. So they sent in a system, of course, to clean out the mess. Maybe Canadian geese at that time, I don't know. But they cleaned up everything, did some calibration tests, and they could not get rid of this uniform hissing background. And this is their apparatus version of this, only sort of cut down. And it moves so they could look everywhere in the sky. And they measured the black body spectrum in the microwave region. And they got a Nobel Prize, Wilson and Penzias, for this discovery, which is very unfortunate because there was a U of M graduate professor at Princeton who actually had a graduate student who built a small microwave antenna to actually try to measure the black body radiation of the universe, which had been predicted by various models. And these two scientists at Bell Labs, just by accident, discovered it. This is the way most things are discovered, as you know, by serendipity and dumb luck. Actually, not dumb luck, smart luck. You got to know what you're looking for. That's the difference. Most discoveries, just by their nature, they're unexpected, right? Are made by accident, but controlled accidents, people that know what they're doing. Light is an electromagnetic wave, has electric magnetic fields that are oscillating. It has wavelengths associated with it. Commonly, we know radio, of course. Our radio antenna is big, meters, so that's the wavelength of radio. Microwaves, your microwave oven, if you look inside, it's got a little tiny opening. That's the wavelength of the microwaves, centimeters, fraction of an inch or an inch. So they looked over here, and there's a window in the atmosphere that lets microwaves come through. So they looked out here, and they got a portion of the black body spectrum. And you can see down here, if you detect microwaves that look like black body, you're way down here in temperature, kelvins, which is minus 450 degrees Fahrenheit. Your pipes will freeze. And then over here, of course, as we go up, we have our visible spectrum, which is our sun, which is right here. And that's where we're looking right now. So right now, you're looking at wavelengths of 500 nanometers or half a micron, micrometer. And the frequency your eye is detecting through chemical reactions is 10 to the 14th cycles per second of the electric field. But it's really not detecting the frequency, it's just absorbing the energy at that frequency, which causes chemical reactions in your eye and signals, etc., which is amazing in itself, of course. But they detected a microwave background, which was way down here. So we're here in the visible. If you dull red object like here that you don't see, it's invisible, it's infrared. Here's the surface of the Earth. Also, you have to look in the infrared. So there are satellites, infrared satellites looking at the Earth right now in the infrared to look at various things. And what they detected was a microwave black body spectrum corresponding to a temperature of the universe of 2.7 degrees Kelvin, which is minus 270 degrees Celsius or minus 455 degrees Fahrenheit. Extremely cold, as you might expect. You don't want to go out there for spring break. In fact, the black body spectrum, now seen by satellites, you have to get above the Earth's atmosphere to see the real details of the microwave spectrum. It's the best black body spectrum known to man. It fits within a fraction of a percent to what's called the black body spectrum. It's a perfect emitter. The universe is a perfect black body emitter, the best we know of. Okay? In fact, you can use this to test all kinds of theories. This is from a new satellite, COBE, and here's the more accurate value of the universe, 2.74 degrees Kelvin. Okay, so we have a temperature for the universe. Do we have a good model for the initial temperature of the universe? Remember, the temperature of the universe is between the stars here. We have to look between stars, and these are all galaxies, by the way. We have to look between these things to get the temperature, and that's what was done with the microwaves. So do we know how the temperature changes with time? How did the universe start, at what temperature, and how did it cool off with time? So we have the cooling curve, and we know the present temperature. We can estimate the age of the universe. Well, yes, again, due to nuclear reactions being studied and understood, we know sort of how the universe started. So we have the Big Bang model of the universe, in which case we started with primordial quarks, which we have now discovered and know about. Quarks form neutrons and protons, subatomic nuclear constituents, and that takes so much energy, so much temperature for that to happen. And just like when you make something and drops condense out, well, nuclei condense out at some time scale, and it's very quick. It happens in seconds. And then as you get down here, at this temperature here, nuclear reactions stop. You can't have quarks making nuclei when you get down in this region. And in fact, when you get down to this region here, which is sort of like the sun's temperature, atoms become stable. That is, protons and electrons combine to form hydrogen. If you're warmer than that, they come apart. So we know that at this point here, 700,000 years after the Big Bang, assuming this model, then you have atoms being formed, hydrogen being formed, from which you can start making matter that we know about. So here's a time scale, and here's a temperature and a time. So there's our initial cup of coffee, if you like. So in this model, we have the universe starting t equals 0. Here it is, actual size. True. How can I get all the mass in there? E equals mc squared. It's all energy there. So at 3 minutes, we have a temperature of 10 to the 9th degrees Kelvin. Then the universe is going to expand and cool off, and it's just a gas, right? It's cool. I'm not going to do it again. Okay. If you can feel it, it's very cold. So as a gas expands, it cools off. And we can see that, I guess. This one is less noisy. It's OK. So we're going to expand carbon dioxide gas. Oh, yeah, thanks. He's going to get back at me for that. OK, here we go. Yep, CO2, dry ice. There we go. So here we have condensation of gas to matter, which happens in the universe. Same physics, and we know how that happens. There's gas laws that tell us how it happens, and we can do that experiment. OK, here we go. Expand the universe for me. There we go. And it kind of expands at the speed of light there to begin with, and it kind of slows down. So we have some nice models, including Hoberman spheres, that tell us all about expansion laws and how gases expand. So then we do that, put that in for our cooling model, where the universe is now a certain size that we can measure with telescopes. 2.7 degrees Kelvin right now. We get an age of 12 to 14 billion years for the universe to cool off. And it's going to keep cooling. That is in pretty good agreement with the cooling curve for white dwarf stars, which is total independent measurement, 12 billion years. OK? What about the Earth again? So let's get back to the Earth. So is the Earth 12 billion years old? Or was there some recycling, reprocessing? So are we recycled? Are we like a second, third generation recycled solar system and planet? That has lots of impacts for evolution, of course, the time scale of evolution. Also, it determines what elements are now formed when we're recycled, because it takes time to build up heavy elements from hydrogen and helium, the light elements, the protons and neutrons. So that actually will impact what life looks like, because you have to have certain building blocks, certain elements to make life, of course. So the primary method, and probably the most reliable, now I'm biased, I'm a nuclear physicist, is the use of radioactive decay. In fact, the US National Academy of Sciences in the 1920s declared it to be the way to define ages. So we have official documents saying you should use radioactive decay to determine ages. So let's look at what decay is, and does nuclear decay follow a cooling curve or some uniform curve that we've just been using for all these other age determinations. There's another type of related phenomenon, light sticks. So Big Bang, that was a little bang, right? Little bang. This is a chemical reaction going on where I mix two chemicals, just like the Big Bang did, mixing up quarks. And now I've created some unstable atoms here. They're actually atoms in excited states. As they decay, they give off light. Now these are the new giant versions that you can buy. We use them for camping and other things. You can buy them in different colors. Okay? So are the colors important, etc.? This is chemiluminescence, not nuclear decay. Chemical decay. Well, let's look at the light output. So maybe I want to know, when did I just break the light stick and get it started? What could I do? Turns out I could measure the light output. Now your eye is not linear, it's logarithmic. It's a nonlinear because of the wide variation you need. So I have to have an instrument like this that doesn't measure temperature, that would measure light output in some absolute scale, which we have. So if I watch the light, if you bought these, of course, thinking they would last a week, you're surprised when they only last a few hours. It does depend on the color you buy. So some are short-lived, some are long-lived. The Air Force likes to use these in various night vision applications, so they've actually measured all this data. So they've bought a bunch of light sticks, different colors, and guess what? The light falls off exponentially. Do you get a pattern here? Okay. And there is a baseline, though, so you've got to take that into account. Okay? So this is a good example of a decaying system, if you like. They're chemiluminescent atoms decaying. So in fact, given a certain light output, absolute light output. So I have to know how many chemicals were in here to begin with, the two chemicals that I interacted. I have to know that to tell me how much light I start with. So I'm going to have to know some initial conditions. I can, from the light, the same here, and depending on the light stick, deduce the time since I started the light stick. So you can watch this decay if you get bored. And we'll see what it is after an hour. So let's talk about a nucleus. So we're going to go into some nuclear physics. Well, those were atoms, so here's a nucleus. And one nucleus we're interested in is carbon-12. Carbon-12 is an isotope of carbon. In the middle of all these electrons on the outside, you have 6 protons and 6 neutrons. 1, 2, 3, 4, 5, 6, okay? So 6 and 6 gives us 12, and that's the stable isotope of carbon-12. That's the primary form of carbon. It's in the carbon-12 nucleus. Now, the only thing that determines chemical properties are the number of electrons, and those are always 6 for carbon. Hence, carbon has 6 electrons always. So the chemical properties determined essentially by the number of protons, because that's the number of electrons. Yet the nuclear properties and the nuclear decay properties in particular, the radioactivity, is going to depend on the number of neutrons. So let's see. In this case, we have equal numbers of protons and neutrons, and carbon-12 is stable, very stable, as far as we know. But there's another version of carbon that has a few extra neutrons. It has 8 neutrons versus 6 protons. Those neutrons actually would like to be protons. So 6 protons and 8 neutrons makes carbon-14. Is carbon-14 stable? No, it's not. We can get into details, but the neutron would like to become a proton, but it has to do that very slowly. Here's some quarks. So you have a down quark wants to become an up quark through a weak interaction. There's a Feynman diagram. Fancy, fancy, fancy. Let's not worry about it. But this takes place pretty slowly. And for example, phosphorus, which is another well-known radioactive nucleus, decays to sulfur, 32. It does so with this so-called half-life of 14 days because this is a weak interaction that does that. And there's all kinds of nuclei that decay this way, and they emit an electron. And the electron doesn't come from the atomic electrons, it's coming from the neutron in this model. So the neutron ejects an electron, and it's inside the nucleus, and the neutron becomes a proton. So in a sense, the nucleus is cooling down because it wants equal numbers of protons and neutrons. So it cools off by getting rid of an electron and having a neutron become a neutron become a proton. In this case, carbon-14 beta decays, because beta is the term we use for electrons that are decaying out of the nucleus, discovered by Madame Curie, becomes nitrogen-14, which is a gas. And nitrogen-14 is stable. It has now equal numbers of protons and neutrons. So carbon-14, the isotope carbon-14, decays to a new nucleus, a new element, nitrogen-14. This is alchemy, right? We're changing elements. You can change lead to gold. I can do it by doing a nuclear reaction. So I could also send an electron in and stick it on nitrogen-14 and make carbon-14 if I wanted to with an accelerator. It takes some energy, though. Okay, the conversion of neutron to proton and N14, the rate at which the electron comes out, the rate at which a neutron decays, and the amount of carbon-14 that decays at any given time, or the rate of decay, just like the rate of the light output here, the number of atoms decaying here, is going to follow a curve, and guess what? Of course, it's exponential. And it's convenient to define a half-life. For the math people, there's the curve. This is the initial abundance of the carbon-14. This is what's left over at any given time. It follows a curve like that or like that. And we like to introduce half-life because we know in one half-life, we have 1/2 of the original amount of material left, carbon-14 in this case. And half of it has been now converted to nitrogen-14. After 2 half-lives, we have 1/2 times 1/2, or 1/4 left over. After 5 half-lives, we have 1/4, 1/4, 1/4, 5 times, 1/32 of the original carbon-14 left over. So this is nice to use, half-life. So a characteristic of the radioactivity we often quote is the half-life, is this time here, the time that shows up here. More officially, it should be in this equation, but this is more convenient. Okay, so as I just mentioned, after 5,730 years, which is the half-life of carbon-14, we will have half the carbon-14 left. And half of it will have been converted to nitrogen-14. After 2 half-lives, which is 11,000 years, we have 1/4 left, et cetera, et cetera. Hence, we know the original amount in the sample, the amount we started with, just like our light stick over there, and know the amount left over, the amount that's decaying at any given time, we can deduce the age at which the whole process started, the decay process started. So we're going to come back to that later, but let's look at other dating methods for the Earth, the universe, and the stars. We already saw that the Earth is probably billions of years old, the universe is billion years old. We can't use carbon-14. That's 5,000-year half-life. We would have no carbon-14 left, essentially, if we're going to use carbon-14. So we have to find something else. Are there radioactive nuclei that we can use instead of carbon-14 that decay over billions of years? Well, yes. And again, Marie Curie and others studied these nuclei, and she discovered the basic forms of radioactivity, alpha, beta, and gamma. First 3 letters of the Greek alphabet. And alpha, we now know, is the emission of a helium nucleus from a nucleus, a heavy nucleus. Gamma ray is emission of electromagnetic radiation of very short wavelength because the nucleus is a very small antenna. It's femtometers, 10 to the minus 15 meters. The wavelength emitted is proportional to the size of the antenna usually. Just like this is microwaves over here, we know that this is centimeter wavelengths. The nucleus emits radiation which is femtometers, 10 to the minus 15 meters in wavelength. And the beta particle we now know is an ejected electron, alpha, beta, gamma. So Rutherford in the early 1900s proposed using helium to detect heavy nuclei and the decay of uranium in particular because it had been studied. he tried measuring helium gas accumulated in rocks. So all the helium in this balloon comes from the decay of heavy elements, because natural helium does not stay here on Earth in our atmosphere. It has to be down in rocks because, well, whoops, there we go. Hey, bye. It leaves the atmosphere. Helium it doesn't stay in the atmosphere, obviously. It'll come back down later, next lecture. Okay, so he basically went and got some helium in a certain amount of rocks and tried to then use that to measure how much uranium, it turns out helium comes from uranium, how much helium had decayed. So he estimated using helium accumulation in rocks the age of the Earth, and he got a few 100 million years. But there are problems, and all the age determinations, the different rocks he looked at had different ages, a wide variation. But again, he got a somewhat old Earth. But the method was later refined, and in particular, once all the radioactive decays were studied. Now here's a chart of the elements, neutron number versus proton number. Here's a, quote, stable isotope of uranium, but it's not stable. It's uranium-238. It decays with 4.5 billion year half-life. Guess what? That's just the time scale we need to study things that are billions of years old, and that's one of the ones we use. And to do that, though, we have to make sure we understand all these decay branches, how it decays. So it emits an alpha particle, jumps here, some beta particles, more alpha particles are emitted, jumps around here, beta particles, and then ends up in a stable nucleus, lead-206. So the way we do dating of things billions of years old is to look at the ratio of uranium-238 to lead-206 left in a sample. And that's pretty unique measure of the age. We see that this is the longest lived decay in this whole change. This is days, millions of years, thousands of years. Everything down here is pretty short-lived. So the decay rate of uranium-238 and the formation of lead-206 on the million-year time scale is determined by this half-life right here, the first decay. And then we just simply wait until we get here. So that's the basic technique. And now we have models using, again, nuclear reaction rates, things we already know and can measure in the laboratory. At a given time, how much uranium-238 to lead was at a given time in a Big Bang, in an exploding stars, when the Earth was formed, etc. We have models for that. Okay? So one question is just to measure the uranium-238 to lead-206 in a sample. Lead-206 is not the normal version of lead, you see. Normal version of lead is the isotope 208, so we don't have interference here with the stable isotope. This is also stable but rare. It only comes from decay of uranium-238 primarily. So this is a good signature. And there are more of these type of chains we can use. So using this method and using rocks that we find on Earth, and using uranium, actually spectroscopic lines of uranium we see in old stars. First of all, we date the universe from uranium dating, looking at oldest stars. How much uranium and lead-206 do they have? And there's different methods. We use other isotopes. We then get an age of 13 billion years again. So using these long-lived radioactive isotopes, we can measure the age of the universe through stars, the oldest stars, and we get, again, 13 billion years. But what about the Earth, the Moon, and the planets? For example, was the Earth, the Moon, and the planets all made at the same time? Were different planets made at different times, etc.? Was the Earth and the planets made at the same time the Sun was formed? And now we have a method to do this. We have to get samples from all these places and measure the uranium to lead ratio or other isotopes. And this is a technique called clocks and rocks. And you can learn all about it on Hyperphysics again, that wonderful program. And here are some things we might use: uranium-235, uranium-238, potassium-40, rubidium-87. They all decay to fairly unique products, as I mentioned, and they all are present in various types of rocks. So we have a wide range of clocks and rocks we can use to date all kinds of rocks. Okay, so if we look at rocks in Canada, even in the upper peninsula of Michigan, as you drive along, you'll see some very ancient rocks. Some of the oldest rocks on Earth are in the upper peninsula. They were brought down here by the glaciers, amongst other things, or our outcroppings. If we use these isotope ratios, we get, again, that the age of the Earth is 4.5 billion years. In fact, that's so accurately determined, it's known to 100 million years. And there are thousands of measurements of that age. So there's no ambiguity in the age of the Earth, according to most of us at least. Okay? There's an example of the data you get, which is the ratio of strontium, rubidium decay to strontium isotopes. You get these curves. These are all various rock samples. You fit it, et cetera, et cetera, et cetera. And here's the age that he gets to 40 million years, he claims, for those samples. Now, there is some variation of millions of years, hundreds of millions of years in the various rocks, which relates to their kind of history, their early history. But overall, all the oldest rocks on Earth are 4.5 billion years old. Okay, we can now look at moon rocks and Mars rocks. We have meteorites here on Earth that have come down from various places. These are rocks that were in the solar system originally that didn't form planets. So let's look at those. So we go dig them out of a meteorite crater. We find the rocks that are metal. And then we look at, again, the clocks in the rocks. So we can date those, and we find that they are also 4.5 billion years old, within 100 or 200 million years of the age of the rocks on Earth. So these meteorites, which are out there in the solar system, are the same age as the Earth. We all were sort of formed together, born together. Like my twins, we're non-identical twins, but we're sort of twins, generically and genetically. Okay? We also can date the moon and the planets. So we have rocks from the moon and Mars, maybe some rocks from Venus even. Boy, how do we get those? I'll show you. We have meteorites, of course. And they all date to 4.5 billion years within a few hundred million years. So we're all twins, all formed together. This is important to study the evolution of the solar system. We can date all these various objects out there, all the solar system objects. Where did I get the moon? Where did I get moon and Mars rocks? I actually have rocks from the moon and Mars. Well, one option is you go on eBay and find an alien willing to sell you Mars rocks. Or meteorites or moon rocks. Here is a rock from Mars. How did we get moon rocks and Mars rocks here on Earth? Well, they come down as meteorites from those planets. A big meteorite hits the planet or the moon, creates a shower of rocks. Those are light planets and light moons. Those rocks can escape the gravity, and they will end up here on Earth. And how do you find them? Well, you have to look in a place where you can really pick them out, which is a desert, or even better, Antarctica. So many of our moon rocks come from the Antarctica. They kind of stick out, right? If you find a black rock on the snow, it's probably from the moon. If you find a red rock on the snow, it's probably from Mars. And of course, we have space probes that know the composition of these rocks. So we didn't have to go there to find that, although we do have moon rocks, of course. And we find out that, indeed, these are rocks from Moon and Mars. So there, as we speak right now, there are people on snowmobiles running around the Antarctica, probably graduate students, looking carefully for Moon and Mars rocks. So this implies a solar system relatively young, 4.5 billion years. So we are made from recycled atoms and material. We're second, third, fourth, fifth generation stuff. Because we had to evolve from the lighter elements, first and second generation, because we're made of heavy elements. Most of the heavy elements in us come from exploded stars, supernovae, that then get recycled. Supernovae is a way that we can have the nuclear reactions take place that will synthesize heavy elements. Again, we know how these reactions go. We study them in the laboratory. We have models for how stars explode that we can test and see. And they're very good models. They work very, very well. So there's an exploding star. Inside, in fact, is a neutron star, which is another interesting object you've probably heard about in these talks. So here we are. We're just recycled stardust. Amazing. But to do that takes billions of years. How it does that is another interesting question. So a question, is radioactive decay constant with time? You may argue. Maybe the basic constants of physics are changing with time over billions of years. That's a long time. Nuclear decay rates, can they be changed by temperature? A star explodes, do the decay rates stay constant? Temperature? But these are things we can measure in the laboratory. One laboratory is to look back at old stars. Again, we can go back hundreds and millions of years and look at the physics in these old stars. Here's an exploded star we can look at. I'll just go through there. There's a decay curve of cobalt in that supernova that's 200,000 years old. This is a log scale. This is the radioactive decay of cobalt-56 in the star. Again, it tests our model of supernova, and we predict this, in fact, exactly that amount in that type of star, and it decays with 77 days. So it has the same half-life that you would measure here on Earth. So we can look at radioactive decays in old stars, and we see the physics is the same. The half-lives don't change up to these time scales, which are actually up to billions of years. So there's some experimental evidence. So we think that the fundamental constants don't change, hence nuclear decay rates are reliable clocks. But there's a certain decay, electron conversion is called, is very rare. This is where an outer electron, not an inner electron or an electron and neutron, is responsible for decay. The electron sometimes comes into the nucleus and is captured by a neutron, makes a proton or something. That's a very rare decay, and that can change with temperature because this is an atomic electron. So the orbit of this guy can change a little bit with temperature. We see a 1% effect for this type of decay, but this type of nuclear decay is not used in dating generally. So there are some interesting effects you can measure in the laboratory again for certain types of decays, but not generally beta and alpha decay used for dating. To remind you though, the nucleus is very small. If the atom were the size of Michigan Stadium, the nucleus would be a quarter placed at the 50-yard line. So most of us is empty space because all your matter is in the nucleus. So we're just a cloud of electrons again. Sorry, folks. And what happens here doesn't matter, doesn't affect what happens over there. Except every November, I guess. This is why you get a very pure exponential decay curve. In fact, is it really exponential over many half-lives? Well, people can measure that again in the laboratory. So here's some colleagues at Berkeley who took a radioactive isotope and measured over 15 half-lives. So this is a logarithmic plot, and it follows within a percent, an exponential decay curve over 15 half-lives. Pretty good evidence that nuclear decay is understood. So we can extrapolate even for minute amounts of material back along these decay curves. Okay, what about relativistic time dilation? So we have to go to Einstein. We're going to do the twin paradox and see what happens. This is an effect that we have to account for, by the way. Well, let's do it more scientifically. We'll go to Hewlett-Packard and buy an atomic clock. Atomic clocks are clocks which are accurate and can be synchronized to 1 second in 1,000,000 years. So if you came back in 1,000,000 years, they would both read the same time. So here's our twin, because it has a real clock. So we'll put one twin in a jet airplane and send it around the world. And then when that jet plane comes back, since it's traveling not near the speed of light, but not stationary, it comes back and it should have a different time. It should have aged slower. So people have done that, actually. So what did they find? Here's what they measured. It lost billionths of a second, or gained billionths of a second, relative to the ground clock. And here's what was predicted by relativity. So they did the twin paradox, and it agrees with uncertainty. So you can do the twin paradox with some atomic clocks and all those frequent flyer miles you've been saving up. Hence, radioactive cosmic decay is important. Radioactive decay for things traveling near the speed of light is important, and the clocks will slow down, and the decay constants will change for something traveling near the speed of light. This takes place for cosmic rays and is probably responsible for evolution. So I'm just going to go through this briefly. Here's the cosmic ray picture. Cosmic rays come down, they make muons here, which are radioactive. So these muons are radioactive, and normally they would never reach Earth except they're traveling near the speed of light. So only because they're traveling near the speed of light can they reach Earth. Normally they would decay immediately up here, but they can reach the speed of light. And here's some data you can look up on hyperphysics. So it's only through relativity do muons reach the Earth, and these are one of the primary cosmic rays. When a muon goes through DNA, it mutates it. But nature has given us a double helix here, so most breaks in the DNA are repaired, luckily. Because then we'd only need an Earth a few 100 million years old to have evolution, probably. So it takes a double break of the DNA, And most of the double breaks even don't do anything. But once in a while, double break does something bad, does something good, depending on your point of view. It can cause things to change genetically. So that's thought to be one form of evolutionary changes due to cosmic rays. And only those cosmic rays get here, as we saw with our cloud chamber, which we'll turn on later, only because of relativity. And because the rate of mutations is kind of a constant with time, we can actually use DNA mutations as a clock. There's a constant rate of mutations in DNA, so we can trace species development through DNA as well as radioactive dating. So here's the size of brains versus time. You are here. But like most of DNA, most of our brain is probably filled up with relatively useless information. It's just gotten bigger to accommodate more. You know, the internet and all that stuff is just information overload. Okay, so how long have humans evolved? We can use carbon-14 for that. And we can also use mutations in DNA for that. So here's the carbon-14 scenario. Again, we have to have a constant source of carbon-14. We have to know how much carbon-14 is in a living thing. And then after that living thing dies, we can measure the decay of carbon-14. So do we have a source of carbon-14 that we know? Yes, from cosmic rays again. Cosmic ray comes down, makes nitrogen-14, and this can make we make some radioactive things. We make carbon-14 in the atmosphere. Carbon-14 forms CO2 in the atmosphere, but radioactive CO2, along with normal CO2 then. CO2 is taken in by various plants and animals that are living, and as long as the plant or animal is living, there's a constant amount of carbon-14 in that animal or living thing relative to the stable isotope carbon-12. So you look at the ratio of carbon-14 to carbon-12. In a living thing, it's going to be a constant because we're always ingesting carbon-14, including the radioactive carbon-14. So this is carbon-14 dating. Dr. Libby won the chemistry prize in 1960 for this. And once an object dies, you start with this ratio in the object, and then the carbon-14 decays. So after 17,000 years, you only have 12% of this ratio left. So to get the age of organic things, living things that have died, you measure this ratio of nuclear isotopes. And so we are radioactive also. And instead of doctors giving us radioactive stuff, it's nature. But you see, it's a small, small amount. So very little carbon-14. Any radiation from that gets repaired by our DNA. So it doesn't mutate us as far as we know. Okay, but you are a little bit radioactive. So to measure the ratio of carbon-12 to carbon-14, we need very precise mass measurement device. We have such devices called a mass spectrometer. Here's one that runs at 2 million volts. But using carbon-14 measurements, using a mass spectrometer in particular, we can date things back to about 100, 200,000 years now. So there's different techniques you can use. And now we use this new technique primarily for carbon-14 dating. One of the controversies, of course, involved the Shroud of Turin, thought to be the Shroud of Christ. It would date 2,000 years old. The pastor in charge of the shroud let some people take one thread off, and that's all you need if you're going to use mass spectrometer like I've shown. And they dated the thread from the cloth to 1300, 700 years. Now, it's very controversial. Did they get the right piece of thread from a piece of cloth that was the original piece of cloth? Also, bacteria or any other living thing on the cloth will change the age because they will have the higher carbon-14 ratio from cosmic rays. Also, there was a fire, and this thing was in a locked case during a fire. This is what keeps scientists interested and on their toes, because is that the real age? Did it come from 1300s? So is it a forgery from 1300? Or is it really older than the carbon-14 says? Well, this is an active area of research. Still undecided problem. There's another problem. In the 1950s, remember the Cold War? I had to practice every day going under my desk at school, etc., and finding all the bomb shelter signs. Why? Because we had these tests going on. This is a hydrogen bomb test by the US in the 1950s. This, unfortunately, is one way you can make lots of carbon-14. and strontium, rubidium. All those radioactive isotopes we're trying to use for dating are made here in bomb tests. So this is something we have to include. But when we correct all that, we can now trace back human evolution using various of these time clocks, carbon-14 and other methods. And this is 1,000,000 years. You are here again, and here are all our relatives. They're not monkeys, by the way. They separated off. We come back from these relatives down here. And we come out of Africa, according to this model. And again, accurate dating is needed to put all these skulls and bone fragments in the right sequence. So it's important to have these dating techniques. Other important piece of science you can do is see how we immigrated. We apparently started in Africa 170,000 years ago. Then we came over here to Persia, went to Europe, but then some of us went to China. Some of us went over here to Australia. Some of us went here. And then there's some debate. The standard route to North America is thought to be there 12 to 15,000 years ago. We can date artifacts. We can follow people and date them as they come along. But there are some scientists that have tracked some artifacts coming 30,000 years ago. My relatives believe it was Columbus in 1492. I don't argue with them, but no. But there may have been a migration 15,000 years ago through Greenland, Iceland. Lots of interesting anthropology, paleontology, etc. going on. Again, all based on very accurate dating. They also brought their dogs with them so we can trace the dog evolution. So we had terriers up here. We have chow chows and pugs there. And Rhodesian Ridgeback. I didn't see that in the Westminster show. I guess it shows up occasionally. Dingoes, which normally aren't pets, I guess, unless you're in Australia, and a few other dogs. So we brought our dogs with us, and we can date those artifacts also. What happened in North America? That's interesting. We think 13,000, 14,000 years ago, we came over through the ice straits here. The oldest settlement we know of is one called Clovis. That dates to 13.5 thousand years ago. But very controversial, because there have been artifacts now found in Pennsylvania and Chile that are older than the Clovis artifacts. So where did those people come from? Or is there something wrong with the dating there? Again, interesting controversy. Those date back 20, 30,000 years, way before the North American migration through the Bering Straits. So this is a ongoing, vigorous area of investigation. Maybe one of you will find some bones or artifacts here in Michigan that might be even older. Very interesting. Maybe we should start looking. They'd be down pretty deep, though. Okay, I won't discuss magnetic dating. We can use that. That's the province of our geoscientists. We can find out how the continents were formed, when they were formed. We all started as one big continent, and then we split off. We can date and find all that. The Earth's magnetic field flips in time. There's a tippy-top demonstration we'll do after the lecture. So that when the Earth's magnetic field flips, molten rocks at that time and lava flows record the magnetic field of the Earth at that time. And then we have a history of how the Earth's field flips back and forth, and we can trace how all the continents have moved around. So we came from one big continent. Again, evolution. Okay, so I hope I've demonstrated that physics, chemistry, and other basic sciences can provide accurate dating techniques for artifacts, give us a sequencing of artifacts, and answer the age-old question, and here's my pun, how old? So, thank you.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. Remlois Tiffany Endowment, and by gifts from friends of the program.